Hey everyone, and welcome to The Explainer. Today we are going on a really fascinating journey, exploring one of the most ubiquitous, yet completely invisible, marvels of modern chemistry. We're going to start with a classic childhood magic trick that you might actually remember, and we'll end up right in the middle of a complex, global agricultural dilemma. It's a story of incredible scientific engineering, some pretty unexpected environmental consequences, and the really delicate balance we have to strike whenever we introduce synthetic materials into our natural world. Let's get right into it.
Okay, let's dive into this. If you've ever watched a classic science demonstration, like the complete experimental video on water-absorbing polymer demonstration presented by Dr. Kem, you might have seen a teacher or a parent rip open a standard, everyday baby diaper. They shake out the cotton lining to reveal just a tiny amount of this unassuming white powder. Then they pour a whole cup of water onto that powder, and instantly, the water just disappears. The powder swells up into a solid gel, catching everyone completely by surprise. As presenters often point out, it genuinely looks like magic to a child. But as we'll see, what we're really looking at is a highly specific, beautifully engineered chemical reaction.
Section 1. The magic of polymers, turning powder into snow.
Take a product like Insta-Snow, for example. You start with a tiny scoop of white powder, you add water, and within seconds, it literally erupts. It absorbs hundreds of times its own weight in water, expanding massively to form a fluffy, white, snow-like substance. The sheer joy and surprise on the faces of people seeing this for the very first time is just amazing. But as enthusiastic learners, we kind of have to ask, how is this massive physical transformation actually happening? Where does all that water go?
Well, the answer lies right here in this definition. What we are looking at is a superabsorbent polymer, or SAP for short. Let's break that down. Because it isn't magic at all, it's a synthetic, macromolecular, cross-linked hydrophilic chain. Now, hydrophilic simply means it absolutely loves water. You can think of it as a highly engineered microscopic plastic net. It's specifically designed at the molecular level to capture and trap water molecules inside its structure, holding vast amounts of liquid relative to its original tiny dry size.
Section 2. The science of superabsorbents, a molecular net. Now, what's really interesting about this is how a seemingly insignificant alteration in a chemical structure drastically changes the physical properties of the polymer itself. On one hand, we have sodium polyacrylate. This polymer absorbs water in mere seconds to form a soft slush. Because of the super rapid absorption, this is the exact polymer used in baby diapers and fake snow. But on the other hand, we have polyacrylamide. It works much slower, sometimes taking up to 24 hours to fully hydrate, forming solid, clear cubes. Because it releases water slowly over time, this structure is perfect for soil amendments. A tiny shift in the atoms changes the entire real-world application. Crazy, right?
To understand why they absorb water at all, we really have to look at the internal mechanism. Imagine long polymer strands that are covalently bonded or cross-linked together. These cross-links are absolutely vital because they prevent the polymer from just dissolving completely away in the water. Meanwhile, along those strands, you have negative ions, like carboxylate ions. When water is introduced, these negative ions strongly attract the water molecules into the network through a process called diffusion. The water just rushes in, but the cross-links hold the net together, causing the whole structure to swell massively without falling apart.
But here is where the chemistry gets really fun, as brilliantly shown in Dr. Kem's demonstration with the classic hair gel collapse experiment. Hair gel is basically just a hydrogel holding water. If you sprinkle ordinary table salt onto hair gel, you completely reverse the magic trick. Why? Well, the polymer chain is actually more strongly attracted to the ions in the salt than to the water molecules. So, the salt ions bind to the polymer, the water is forcefully displaced and squeezed right out through osmosis, and the gel shrinks and collapses into a puddle of liquid. It perfectly proves that we're dealing with reversible chemical attraction, not permanent magic.
Section 3. Everyday polymer applications, beyond the diaper.
We rely heavily on the mechanical and chemical stability of SAPs across completely different industries. Beyond personal care products and diapers, you'll actually find tiny amounts of them acting as moisturizers in everyday cosmetics and skin creams. In the biomedical field, they're used for precise drug delivery and advanced cell cultures. They're even essential in wastewater treatment for absorbing contaminants. And get this, they are used in construction to create self-curing concrete. Society has quietly built an enormous dependency on these tiny water-trapping nets.
Section 4. Hydrating our agricultural future. Engineering, drought resistance.
Now consider this staggering fact. Globally, agriculture accounts for a massive 85% of all water utilization.
85%. With climate change driving rising temperatures and increasing the frequency of severe droughts, the need for agricultural water conservation isn't just a good idea, it's an urgent, existential priority. If crops can't get water from the soil, they face water stress, yields drop catastrophically, and global food security is threatened.
And this brilliantly illustrates where our slow-absorbing polymer, polyacrylamide, offers a potential solution. By mixing it directly into sandy soil, we completely change the game. When it rains or when a field is irrigated, these SAP beads act as millions of tiny underground water reservoirs. They soak up the excess water that would otherwise just drain straight away into the earth. Then, as the surrounding soil dries out in the heat, the polymers slowly, steadily release that trapped moisture directly back to the plant roots.
The agricultural benefits of this are absolutely massive. Applying SAPs to sandy soils drastically boosts water retention, improves soil aeration and porosity, and essentially buffers the plants against dry spells. In fact, research shows that in certain conditions, using these hydrogels can delay crucial drought stress in crops by up to 105 days. I mean, for a farmer in an arid, drought-stricken environment, this synthetic polymer is nothing short of an agricultural savior, significantly boosting crop yields while drastically reducing the amount of irrigation water they actually need to use.
Section 5. The microplastic complication, an unseen residue. But there is a catch. Recent extensive reviews, such as those published by Cambridge University Press, have brought a really critical complication to light. SAPs are now being increasingly recognized as a largely overlooked class of potential plastic pollutants in our ecosystems. While they start out as these incredibly beneficial water holders that save crops from drought, they don't just magically disappear. Over time, physical weathering and chemical degradation can transform these polymers, changing their intended properties and potentially leaving behind persistent plastic-like solid residues right there in the earth.
To put this scientific reality into perspective, check out this statistic. Studies have shown that the degradation rate of certain polyacrylate chains in the soil can be incredibly slow. We're talking just 0.12% to 0.24% over a 6-month period. That means the vast majority of the polymer remains in the soil long after the harvest is done. And while researchers are urgently looking into biodegradable alternatives made from starch or cellulose, right now our primary tools are synthetic polymers that degrade at an absolute glacial pace.
Which brings us to the crux of the whole issue. We're left with a profoundly complex trade-off. How do we balance the incredible agricultural salvation provided by SAPs, their amazing ability to save water, fight drought, and feed growing populations, with the very real risk of creating a lasting legacy of persistent microplastics in our soil? It's a powerful testament to the fact that everyday scientific miracles are rarely simple, are they? I really encourage you to think critically about this as we continue to innovate our way out of global challenges. Thank you so much for joining me on this explainer, and keep exploring the science around you.